All right, we'll cover section 4.1 on exponential functions. So what is an exponential function? Well, an exponential function has the formula b to the x, where b is a constant and the variable is x. B, that constant, is called the base of the exponential. So a good example is the function 2 to the x. This is an exponential function with base b equal 2. So the variable for this function, x, appears in the exponent spot, which is where exponential functions get their name. Here's a non-example. X squared is not an exponential function. Even though there is an exponent, this is a power function because the variable x is not in the exponent. Okay, so we want to study the graphs of exponential functions, and we'll do that first just by point plotting. So we'll look at the graph of f of x equal 2 to the x. So we'll plug in the x values -3 through 3 and see what the y values are. Okay, so 2 to the -3, well, you have to remember the rule of exponents here. That's 1 over 2 cubed, so that's 1/8. 2 to the -2, that's 1 over 2 squared, and so that's 1/4. This is 1/2. 2 to the 0, well, any number other than 0, when raised to the 0 power, is defined to be 1. 2 to the first is 1, 2 squared is 4, and 2 cubed is 8. So we'll just plot those points and connect them up with a smooth curve, and this is our general idea of what the graph of f of x equal 2 to the x looks like. Okay, so there are 3 important features that we're going to try to record for any exponential function. We want to record the horizontal asymptote, and for 2 to the x, the horizontal asymptote is y equals 0, aka the x-axis. It almost looks like the graph is touching, but that's an artifact of this plot. The graph never actually gets all the way down to y equals 0. The second feature that we're going to record is that on the side of the graph that isn't approaching the asymptote, we're going to record that it is going up. So I refer to this as right arm up. And I'll also just parenthetically say that it's going up very rapidly. And the third important feature that we're going to record for any exponential is the y-intercept. And here, again, it's because 2 raised to the 0 power equals 1. The y-intercept for this graph is y equal 1. Okay, so now we're going to look at other exponential functions, and we're going to break them into 2 different classes based on whether the base, b, is a number that's bigger than 1 or a number that's between 0 and 1. Okay, so here are the some graphs where some exponentials where the base is bigger than 1. 2 to the x, 3 to the x, 4 to the x. So the color coding here, 2 to the x is right arm up. 4 to the x is rising even more rapidly, as you might expect. Okay, again, all we're really going to be focused on are these 3 important features. And what you can see is that they're all identical. It doesn't matter what this base is. If it's bigger than 1, these 3 important features are going to be the same. All of these graphs have y equals 0 as a horizontal asymptote. All of these graphs are right arm up. And all of these graphs pass through the point 0, 1. That is, their y-intercept is 1. Okay, so remember this, when the base is bigger than 1, this general shape for an exponential. Okay, and then if the base is between 0 and 1, so here's a collection with base a half, a third, and a quarter. Well, what we see this time is now it's left arm up for the graph. As we move left to right, the graph is falling. Okay, so we have a little bit of a swap here. We still have the y equals 0 is the horizontal asymptote, but now that's taking place on the right side of the graph. And the other side of the graph is now left arm up. And once again, any non-zero raised to 0 equals 1. So the y-intercepts for all of these graphs are 1. Okay, so the 2 basic forms that you want to be thinking about just are dependent on whether the base, b, is bigger than 1 or between 0 and 1. Okay, so we're going to look at transformed exponential functions, and we'll be doing this a lot in this course, looking at the exponentials, logs, and trig functions, and transforming them all in various ways that you've studied before in a college algebra class. So I encourage you to go back to section 2.6 of your text and try to review some of these graph transformations, vertical shifting, horizontal shifting, and so on. So before we do this, one of the vertical scaling, we just need to review this precedence between negation and squaring. And I've seen this trip up students quite often. So pay special attention to this and try not to make this error yourself. So if we put -3 in parentheses and square, what that equals is -3 times -3, and the negatives cancel out and we get 9. But absent the parentheses, the precedence operation here is that we first square and then apply the negative sign. So these two expressions are not the same, and it's really important that you not get confused, that you don't want to think that -3 squared in this form is equal to 9. And similarly, of course, you don't want to make the other mistake either. So we want to square before we apply the negative when we're looking at this expression. Okay. So that's the distinction I wanted to make clear here. This -2 to the x is something very different than that expression, right? So what we're trying to study here is the effect of putting a negative in front of our formula for 2 to the x. And once again, what we're going to be focused on is simply the three important features of the graph. So the three important features for 2 to the x, we already know what they are. And now we just ask ourselves, what's the effect of putting a minus sign? Well, all of the y coordinates are going to be negated. And graphically, what that means is the graph is going to flip over the x-axis. Now, when that happens, the the horizontal asymptote is not going to change. We're going to have a drastic change in the other arm, though. As we do a vertical flip, now we're going to have right arm down. That's the flip here. And as we flip over the x-axis, the y-intercept is going to go from 1 to -1. Okay, so here's the hand sketch of this graph. And again, when you're asked for a hand sketch, all you need to worry about is giving the three important features. Need to be just a little wider here. Sorry about that. Right, so this is the mental picture here. You want to be really confident on the graph of 2 to the x, and then just think your way through what's the effect of the minus sign. We get this vertical flipping. We're showing the horizontal asymptote by having the graph get close to the x-axis on the left. We're showing right arm down, and we've put a tick mark and labeled it on the y-intercept. And you don't need any of the tick marks. This is going to be a perfectly adequate sketch of the graph. Okay, let's look at vertical scale. So what we're going to do now is this, again, this is a review, but what happens when we multiply a function by some fixed constant? This is vertical scaling. So what's going to happen is that all of the y coordinates are going to get 3 times bigger, scaled up by a factor of 3. And graphically, this means that the graph is simply going to get vertically stretched, right? So what's the effect on the important features of this graph? Well, if we multiply by 3, the horizontal asymptote won't change. Multiplying 0 by the number 3 still gives you 0. This graph is going to get vertically stretched, but that means that the right arm will continue to go up. In fact, it'll go up faster. And then when we multiply all y coordinates by 3, the y-intercept will also get multiplied by 3. Okay, so here are the sketches. Again, this is the mental image that you want right away for 2 to the x. And then when you multiply by 3, essentially the only thing that's going to change is the scaling on the y-axis. And so this intercept now just gets labeled with 3. The graphs, in fact, looked identical except for the labeling of the y-axis. Horizontal asymptote on the left, right arm up, tick mark at 3, exponentials. Your book considers some others like horizontal flipping and horizontal scaling, but the last one that we're going to look at is vertical shifting. So this happens when we add or subtract a constant from the function. So when we compare 2 to the x and 2 to the x minus 3, well, in the second graph, all of the y coordinates are going to be decreased by 3, and that's going to shift the graph downward by 3 units. So we just, again, focus on the important features. The horizontal asymptote was at 0, but the -3 is going to shift that down to a horizontal asymptote at -3. This vertical shifting is not going to affect the fact that the right arm is still up. And let's see, the y-intercept, well, it was at 1. It's been shifted down by 3 units, so now it's going to be at -2. Okay, so here's our hand sketch. So when the horizontal asymptote is something other than the x-axis, I would like you to sketch it in as a dashed line. So you're going to put in this horizontal line, dashed line at -3, and you need to label that tick mark as -3, or maybe you just label here over on the right, y equals -3 is the formula. The graph is getting close to the asymptote on the left. The graph is right arm up, and the y-intercept has been marked with the tick mark and labeled with the correct number, -2. So again, that's a good hand sketch. Soon we'll get to trying to label the x-intercepts for exponential functions as well, but we're not doing that yet. Okay, so this is sort of the culmination of those 3 independent things, is that we're going to look at combinations of transformations. So when you're asked to give a sketch of an exponential or transform exponential of this form, what you want to do is try to process the 3 numbers, the b, the a, and the c, in this order. First, focus just on what the base is, and then look at the a number and then the vertical shift. Okay, so we're going to sketch this graph, give a hand sketch, and it has this form. So the first thing to look at is the base, b. 4 is bigger than 0. I'm sorry, it's bigger than 1. So we know that for any base bigger than 1, b to the x, we know these 3 facts. In particular, since b is bigger than 1, we have right arm up. Horizontal asymptote 0, y-intercept 1. Okay, now we're going to look at the effect of the a number, multiplying by -2. Well, the multiplying by 2 is doing a vertical scaling, but the negative is going to be doing a vertical flip, right? So we're going to scale by 2, but we're also going to flip. That means that the new y-intercept is going to be -2. Multiplying by -2 is not going to affect the horizontal asymptote. And oops, the fact that we're multiplying by a -2 is going to cause a flipping. So this is going to be right arm down. Okay, and then we'll deal with the C number, the shifting number. Okay, so comparing this graph with this graph, let's see, the intercept was at -2, but we're shifting up 3 units. So now the intercept will be at 1. The horizontal asymptote was at y equals 0, but we're shifting up 3 units. And the vertical shifting is not changing the fact that we're still right arm down. Okay, so to give a hand sketch, we just want to include something that shows these 3 features, and here it is. So the horizontal asymptote marked with a dashed line, the y-intercept marked with a tick mark, and we are right arm down. Okay, so sometimes you will be asked for a little bonus information about these functions and their graphs. So based on the graph of this function, we'd like to state the domain and range for the function. Okay, so remember the domain is all of the allowable x coordinates, and the domain for this exponential is -infinity to infinity. You can plug in any x value. When you ask for the range, remember what you're looking for are the y coordinates that are on the graph. And the y coordinates have to be slightly Well, they have to be less than 3 because 3 is this horizontal asymptote that we get closer to but don't actually touch. And then the y coordinates go off to minus infinity. So we have to list this interval from the smallest y coordinate. Whoops. Let's try one more time on that. The smallest y coordinate to the biggest y. And it's an open interval, not a closed interval. Okay, one more example here that'll be in the PDFs, but I'm not going to do it here in the video. Okay, so now we're going to go the other way around. What we just did is looked at a formula, at a function that had a formula of this form and try to sketch it. And now we're going to try to come up with a formula based on a graph, a formula of the specified form based on a graph. So we're going to hope or expect that this graph has a formula that looks like a times b to the x plus c, and our job is to find the numbers a, b, and c. So we're going to kind of reverse what we did in our processing last time. When we were given the formula, we first focused on what the b was, then the a, and then the c. But going in reverse, when we're given the graph and asked to come up with a formula, we're going to process the numbers in the reverse order. Okay, so we're told explicitly that this graph has the formula of this form. And the first thing that we're going to look at is the horizontal asymptote for this graph. And we see that it's y equal -5. And how did we get that -5? Well, it came from the vertical shifting. So that tells us immediately that the C number here is -5. Okay, so now we know our formula is A times B to the X minus 5. And now we're going to use the fact that 0 minus 2 is on the graph. And what that means in terms of the function f is that when we compute f of 0, we are going to get the number -2, right? The x coordinate is the input, the y coordinate is the output. Okay, so what we're going to do now is take our formula. We know the formula has this form, and we're going to replace the x with 0. That is f of 0, and we want that to equal -2. Right? So it's nice that we have the x coordinate of 0 as one of our points, because b to the 0 is 1. So this equation is simplified. We wind up with only a in it. And now let's see, let's add 5 to both sides. And now we know that the a is 3. Okay, so we're on the home stretch here. We know that the a is 3, and we know that the c number was -5. So we use the last point that we were given on the graph. We see that -2,7 is on the graph. That tells us that f of -2 is 7. So once again, we take our formula for f, and we replace the x with -2. That's f of -2, and that's supposed to equal 7. And now our goal is to solve for b. All right, so this is 3. I guess I'm going to go to a form without having a negative exponents. I'm going to add 5 to both sides. What is that? That's 12. And then I guess I'll clear denominators. So multiply both sides by b squared. Divide by 12. Wow. And then let's see, lastly, what are we going to do? Take square roots. So we take the square root of 1/4, we get half. So it has to be positive half because we can't have a negative base for an exponential. So the final answer here is that the formula for this graph looks like 3 times 1/2 to the x minus 5. And just as a quick check here, having this base between 0 and 1 that looks good because what we are seeing here is a falling exponential, one that has left arm up. So that seems consistent with our answer. Okay, another example here that will just be in the PDFs, not in the video. Okay. The last topic for this section is an application of exponential functions trying to compute compound interest. So as a review and an intro to this topic, I just want to think about trying to increase a number by a certain percentage. And the way to do that is to multiply by 1 plus r over 100 when r is the percent. And hopefully an example will make sense here. So to increase 100 by 5%, you multiply 100 by 1 plus 5 over 100. And you don't need to write it that way. You can also just write it as a decimal. You need to multiply by 100 by 1.05, and then you get 105. Clearly, 5% increase. Right. Increase by increase 100 by 6%, and then increase that new number by 6% again. Okay, so to increase 100 by 6%, we're going to multiply by 1.06. That'll be the first increase. And then we're to increase that number by another 6%. And to do that, we'll multiply by 1.06 a second time. And taken together, we can do both of these increases by taking 100 and multiplying by 1.06 squared. And I guess we can look at that as a decimal. 112.36. Okay. Increase 100 by 7%, 10 times in a row. Oh, I've got the wrong number here. I changed one, but didn't change the other. Let's change these. So to increase by 7% 10 times, you need to multiply by 1.07 10 times. So we started with 100, and we're going to multiply by 1.07 10 times. And this turns out to be what I think is a surprisingly large number, nearly 200. Okay, so that's the backstory for trying to compute compound interest. So a bank offers a savings account with 12% annual interest. This means 12% annual interest, compounded quarterly. How much will an investment of $1,000 be worth after 1 year? Okay, so compounded quarterly means that the bank isn't going to give you the 12% all at once. Instead, they're going to give you 1/4 of that 12% each of the 4 quarters of the year. That is 4 times a year. So it's too bad they don't give you 12% each time every 3 months, but they only give you 1/4 of the annual interest rate. Okay, so this is what we did as a review. To increase a number by 3% 4 times, you're going to take that number and multiply by 1.03 raised to the 4th power. So at the end of the year, the amount in the account will be $1,125.51. Okay, so one additional idea here is looking at what happens in the same situation, compounding quarterly, but now we're going to go out 7 years. Instead of just 1 year, we're going to go to 7 years. So we're going to be increasing the account by 3%, 4 times a year. That's what quarterly means, for 7 years. And the last idea here is that in total, then, we will have 28 compoundings of interest. The number per year times the number of years we go out. So our $1,000 is going to be, over the course of these 7 years, our $1,000 is going to be increased by 3% 28 times. Leaving us with a total of, well, roughly $2,300. Okay, one more formula, or one more example here, again, just in the PDFs. Okay, the formula that we've been kind of working up to here, and there's no reason that you can't put this on a note card, is the formula that gives you the amount in an account that starts with a principal of P, has an interest rate of R, is compounded N times per year, and the T here is the number of years. So I hope the examples have made this sort of clear here. When we had 7%, what was it? It was 7 years with quarterly, the 7 times 4, this is the number 28 in the example that we just did. Okay. It's important that the interest rate that you use in this formula is presented as a decimal, not as a percent. So R is the interest per year, N is the number of compoundings per year, R over N, remember this is the percent added each compounding period. And to add that amount, you multiply by this number, and then this is the total number of compoundings. I guess we're doing one more example here. Okay. So 500 is invested at 8% annual, I guess I should write, compounded quarterly. Give a formula for the amount after T years, and then compute A of 2. All right, so to use the formula, we just need to identify the players here. 500 was the principal, 8% was the annual interest rate, again, written as a decimal. The number of compoundings quarterly in 1 year, we get 4. And then the T here is just the number of years. Right, so this is the formula. Just written out with these players. And then for part B, we just plug in T is equal to 2. Just working it out on the calculator. All right, last topic. I hope you're still with me here. We want to talk about annual percentage yield for an investment. So this has to do with percent increases. And so we just want to make sure that we're familiar with that. If we're trying to find a percent increase from 100 to 105, the answer here is 5%. Okay, so the APY for an investment is the percent interest earned in 1 year, A for annual. So we'll do a quick example here. Let's compute the APY for 6% compounded semi-annually. So what we're going to do is compute how much money we wind up with on a $100 investment at the end of 1 year. So here's the formula. We start with 100. Semi-annually means that we have N equal 2 compoundings each year. So we only get 1/2 of the 6% each time. And in, just remember, this is 1 year. So in 1 year, we'll have the 2 compoundings. So we started with 100. We ended up with $106.09. It says the percent earned in 1 year was 6.09. So this is the general formula. If you just want to put it on a note card, it's what we just did here for 6% and N equal 2. We subtracted the 100 off in our heads, but if you want it as part of the formula, that's just a reminder to subtract the 100. Okay, so one of the reasons we're interested in APY is it helps determine which of 2 investments might be the better opportunity. So which of these 2 investments is better? Well, 6% is higher than 5.95, but this, in the second one, we're compounding more often. All right, well, we just computed the APY for the first option, and we got that it was 6.09. And here's the computation for APY for the second option. So compounded daily, says we have 365 compounding periods. Right? So in 1 year, we compound 365 times. We get only this fraction of the interest each compounding period. And for this calculation, we see that the APY, again, we're subtracting off 100 in our heads, is 6.13. So it turns out that the option B, even though it has a lower annual rate nominally, it's a slightly better investment for us. And that's a good place to end the video.